Today, I will talk on heat utilization in furnaces. Complete heat balance of a furnace shows how the heat flows into the furnace. That means, the complete heat balance of a furnace it contains a sources of heat input, Now, these sources could be combustion of fuel, and sensible heat of air or fuel. These are the heat input terms, and sources of heat output. They comprises of, for example, wall losses, then opening losses. In fact, all type of losses which are possible on operation of the furnace. It could also be losses from the hearth losses, and then heat carried by POC. Now, in controlling combustion or in analyzing means to improve economy of fuel utilization, it is required that we consider heat quantities separately. There are heat quantities which relate to fuel consumption, and there are heat quantities which relate to the process. That means, we have to distinguish the heat quantities. Related to process, I mean to say, suppose we are carrying out heating of a billet, bloom or slab, or we are carrying out melting, or we are carrying out refining, or we are carrying out roasting, smelting. That means, whatever metallurgical function we are carrying out, or for example, in the cement industry, you are carrying out calcination. So, there are certain quantities which directly relate to the process or to carry out a thermally derived function, which could be calcination, which could be roasting, could be smelting, could be refining, could be heating only. Then there are heat quantities which are related to process combustion. That means, these quantities, they relate to combustion and they tell us the consumption of fuel. So, we have to distinguish from the heat balance the two type of quantities, and accordingly that will help us to analyze the heat utilization in furnace. That means, we must be very clear in our mind that there is certain quantity of heat which will utilize for the process, certain quantity of heat which will be utilized for combustion purposes. So, now in analyzing utilization of heat from fuel combustion, it is not only amount of heat important, but it is also the temperature at which that particular amount of heat is available is also important. That means, when we want to analyze utilization of heat from the combustion of fuel, then it is the temperature as well as the amount of heat, both are important issue. For example, we want to carry out a process say 1200 degrees Celsius, then whatever type of fuel or whatever combustion process we select, excess air, oxygen enrichment, preheating, whatever process we select, it must be able to generate the temperature, so such that we can operate the process at a desired temperature. So, while considering the utilization of heat from fuel combustion, it is the temperature and amount of heat, both are important. Now, in this connection, the adiabatic flame temperature, in short I will be writing AFT, is a very important tool both from indirect and indirect point of view as a criterion for fuel utilization. That means, the calculation of adiabatic flame temperature can give us a clue whether a selected fuel and the condition of combustion will give us the required temperature or not. So, an obvious requirement is, say, an obvious requirement is that the adiabatic flame temperature, the calculated value of adiabatic flame temperature should be greater than furnace temperature. Now, why is it so? If adiabatic flame temperature is equal to furnace temperature, then no heat transfer will occur and the charge will not be raised to the desired temperature. Therefore, it is quite obvious, then we proceed to select a fuel and combustion process. The adiabatic flame temperature so calculated must have a higher value than furnace temperature, because all of you know from the lecture 1 where I said sources of energy, that the mechanism of heat available from combustion of fossil fuel is in terms of the heat of products of combustion. That means, it is the products of combustion that gives its heat to the charge, that is here heat transfer rate is an important issue. For that matter, adiabatic flame temperature must be greater than furnace temperature. However, higher flame temperature, though desired from the higher heat transfer rate point of view, but higher adiabatic flame temperature can also cause local overheating and can destroy the refractories. So, these things are to be kept in mind, and these aspects I have discussed in lecture 12. In lecture 12, I have also said how to calculate the adiabatic flame temperature, and one or two problems I have illustrated the calculation of adiabatic flame temperature. So, in connection of fuel utilization, the adiabatic flame temperature is very important. We have also seen earlier that adiabatic flame temperature, it decreases with excess air than stoichiometric amount. In fact, if you I will just once again I will draw a schematic here I will take AFT, you can take in degree Celsius or in degree Kelvin, doesn't matter, and here I take percentage of theoretical air. So, somewhere here I will correct 100%. So, this side is less than stoichiometric, less than stoichiometric air, and this side is greater than stoichiometric air, greater than stoichiometric air. So, or you can also call that beyond 100% this is the excess air. So, we have also calculated in lecture 12 how the amount of air above stoichiometric decreases the flame temperature by taking one example. Now, here say if I want to show, it starts from 0 and as you increase the amount of air, then the adiabatic flame temperature attains maximum value at theoretical amount of air, and then it again begins to decrease as you increase the percentage excess air. So, this is, I mean, this one can calculate and one can show. So, what is important here from the utilization of fuel point of view, what is important? The control of excess air is important. Control of excess air is important. Now, as I have pointed out in my lectures 9 to 12, which are on combustion and material balance, I have said over there that in reality the complete combustion does not occur with exact stoichiometric amount of air because of certain practical difficulties which I mentioned earlier. If you have the gaseous fuel, around 4 to 5% excess air is required. If you have liquid fuel, the excess air may go around 15 to 20%, whereas a solid fuel the excess air may be as high as 40 to 50%. So, what is important is the control of excess air is a very, very important issue in order to utilize the fuel or in order to increase the coefficient of utilization of fuel. In this connection, also it is important air leakage. Air leakage is also an important issue. Is also an important issue from fuel heat utilization point of view. What is said over here? That though the combustion requires excess amount of air, but through the proper design of the combustion system, proper maintaining the mixing and so on in the combustion chamber, the excess air should be kept to the minimum possible. Even the operation carried out with the minimum amount of excess air, care should also be exercised so that no air leakage can occur, because the furnace says, that is why the furnace slightly operates slightly above atmospheric pressure to avoid the air leakage. So, that is an important thing. Now, another important thing is the critical temperature of processes. Critical temperature of processes. Critical temperature is the minimum temperature which is required to carry out a process. So, I will write again, critical temperature is the minimum temperature required to carry out a function. For example, if we are having say continuous melting of metals, continuous melting of metals or refining, we have to make sure that the entire process chamber is maintained at least at a temperature to the melting point of the metal. Slightly above will be good, but the minimum temperature that the furnace should have is the melting point of the component. For example, if you are melting copper, then the minimum temperature that the furnace should have is of the order of 1083, but well, slightly excess is required in order to have a uniform temperature. Now, for example, so if we are say in batch reheating, say in batch reheating furnaces, in batch reheating furnaces, the temperature should be at least equal to the temperature at which we want to heat, for example, slab, bloom or billet. For example, if you want to heat the billet for thermomechanical processing or heat treatment purposes to a temperature of 1200 degrees Celsius, then the critical temperature of the reheating furnace is 1200 degrees Celsius. So, that is what the critical temperature is, the minimum temperature at which the function is to be carried out. A similar example can be given, say if we use say processes say which use liquid metal or liquid slag then the critical temperature in this case would be the pouring temperature of liquid metal. If it is slightly lower, then you may not be able to pour the metal. The critical temperature for liquid slag is that the free running of slag, otherwise you will not be able to tape out the slag. So, that is what the concept of critical process temperature is. In calculation of the heat utilization, it is important for us to know what is the temperature at which the process is operating. In cases or in the problems where this is not known, then the concept of critical temperature has to be invoked and can safely be made assumption that at least the temperature of the furnace is that of critical temperature. For example, it is melting of metal, then the melting point, or liquid metal, it is the pouring temperature, and so on and so forth. So, what it is said is that critical temperature has significance in relation to utilization of heat from burning of fuel. That means, the critical temperature is the lowest temperature at which the flue gases will exit the furnace. Now, as all of you know, from the mechanism of heat available from fossil fuel combustion is through the products of combustion. A flue gas temperature, say, which is lower than furnace temperature, or a flue gas temperature greater than furnace temperature, or a flue gas temperature equal to furnace temperature. Now, what I mean from here, that in fossil fuel fired combustion furnaces, three conditions can arise. A flue gas temperature can be lower than the furnace temperature. What does it mean? That means certain part of the furnace are underheated. That is not required. Another condition can occur, a flue gas temperature can be greater than the furnace temperature. When it is possible, can you think of? A flue gas temperature which is greater than the furnace temperature, that means your furnace is not at uniform temperature. Certain part of the furnaces are overheated and the flue gas are living at temperature higher than the process critical temperature. So, both conditions are not desirable. What is ideally desirable? A flue gas temperature equal to furnace temperature, that means your entire process or entire furnace is heated at a uniform temperature. You may consider it is a ideal condition. Now, from here we can invoke a concept of available heat. So, let us say what is an available heat. Available heat. It is known, as I said repeatedly, that the heat carried away by the POC at the process critical temperature is not available to the furnace operator. This heat should not be considered as loss. It is not like wall losses or opening losses, but it is the inherent feature of the thermal energy derived from fossil fuel combustion. So, considering that, we can define the so called gross available heat. Gross available heat, or in short GAH, that is equal to calorific value of fuel, CV of fuel, minus heat to POC, minus heat to POC. You may also consider gross available heat is the heat given by POC in cooling from flame temperature to the critical temperature of the furnace. That means, on combustion, the products of combustion will be raised to a flame temperature, and the products of combustion cool to the process critical temperature, and the heat which is given in this cooling is in fact the gross available heat. That is, one can calculate both ways. One can also calculate, you know, the calorific value and subtract it the heat carried by the POC, or you can also calculate the heat released in cooling the products of combustion from flame temperature to the process critical temperature. Now, for example, if we assume, say if we assume that Cp of POC does not vary significantly with temperature, in the range we are talking about, then one can write gross available heat would be directly proportional to TAFT minus T critical, where TAFT is the adiabatic flame temperature and T crit is the critical process temperature. Critical process temperature. Now, we can further define, say, gross available heat in percent of total heat input, percent of total heat input will be equal to approximately. Now, this approximately is coming because we have taken Cp to be slightly independent of temperature in the range of cooling from flame to the critical process temperature. So, that will be equal to TAFT minus T critic divided by TAFT into 100. So, this is the gross available heat in terms of percentage total heat input. Now, for example, let us take TAFT is equal to 1200 degrees Celsius and our T critic is also 1200 degrees Celsius. That means, if we require a furnace temperature of 1200 degrees Celsius and if the combustion process generates 1200 degrees Celsius as the adiabatic flame temperature, this combustion process is useless from the heating point of view, because there will be no heat transfer and nothing will happen. This particular combustion process, it cannot be used for a metallurgical function. A TAFT that is equal to 1600 degrees Celsius, then the combustion process is approximately 400 upon 1600 into 100, that is equal to 25% efficient. 25% efficient. Now, can you get a feel the importance of adiabatic flame temperature calculation that I have illustrated also in my lecture number 12. Now, you can see from here how far the calculation of adiabatic flame temperature can help in selecting the fuel and in selecting the combustion process. In this particular example, if you are given a certain choices of fuel and choices to make up the combustion system, and if you have assumed a certain value of the heat transfer rate, then you can select the type of fuel. In this particular example, an adiabatic flame temperature of 1600 degrees Celsius, in that case the combustion process is 25% efficient. Now, another say example, if we take, if TAFT is equal to 1800 degrees Celsius, then combustion process would be 600 upon 1800 into 100, that will be 33% efficient. So, if we take now T critical as say 1000 degree, then the same AFT will give little higher efficiency. So, what this calculation suggests, that adiabatic flame temperature is a very important parameter for fuel utilization purposes. From the calculation of adiabatic flame temperature, one can select the type of fuel, because that type of fuel is useful, which can give you, for example, if you want 25% efficiency or 30% efficiency or 40% efficiency, accordingly one can select or one can make a choice of selection of fuel. Also one can make a choice of selection of the combustion process. With this I mean that the adiabatic flame temperature, besides calorific value of the fuel, is also influenced by the whether air is more than stoichiometric, or oxygen enrichment has been used, or preheating has been done. So, in essence, the adiabatic flame temperature can be used safely as a criteria of selection of the fuel. This criteria can be further also explored in switch of the fuel. With switch I mean, suppose the furnace is operating, for example, with natural gas, and we want to replace by producer gas. Say natural gas is a high quality fuel because it generates a very high adiabatic flame temperature, and a producer gas is a low quality fuel because it generates less adiabatic flame temperature. And if we want to replace, that is, we want to conserve the natural gas resources and we want to replace by producer gas, then by calculating the adiabatic flame temperature, one can find out what would be required if we want to switch over from high quality fuel to low quality fuel in order to conserve the natural resources. The importance of adiabatic flame temperature. Now, one should also remember that the gross available heat, it represents the heat available at critical process temperature. It does not represent heat available to the metallurgical process, because what we are doing in calculating the gross available heat, we are simply considering the heat released by the products of combustion from flame temperature to the critical process temperature. So, it only says that much amount of heat is available to you at critical process temperature, whereas the furnace requirement or the metallurgical function requirement could be different. For example, melting. If you just supply a gross available heat which is calculated on the basis of critical process temperature, then the metal may not melt, because you have not considered the losses which are occurring, because the amount of heat which is being lost through the wall or through the opening, it has to be compensated by extra amount of fuel. Therefore, another quantity is important, which is called net available heat. Net available heat, or in short one can say NAH, net available heat. Now, the net available heat, it can be calculated from calorific value minus heat to POC minus heat losses. All types of losses one has to consider. Now, the amount of heat which will be available, that will represent the heat which is available for metallurgical function, or in that way for any function which you want to carry out. So, the concept of gross available heat and net available heat is a very important from fuel utilization point of view. Depending on the objective, one can calculate either gross available heat or net available heat. Now, say consider a situation where the daily requirement for the process is known. You know that per day basis, I will be requiring that much amount of fuel, or per hour, per day requirement or per month requirement of heat is fixed. Then one can also calculate the consumption of the fuel. Now, let us see how we can calculate, say, fuel consumption. Fuel consumption will be equal to the required gross available heat per unit time upon gross available heat per kg of fuel. So, that will give us the fuel consumption. This is further equal to, say, required gross available heat per unit time upon gross available heat per kg of fuel can be calculated from calorific value of fuel. The calorific value in bracket CV minus heat to POC. Heat to POC can be calculated, say heat to POC, that will be equal to Mi Cpi into delta Ti. So, that is how, where I is the type of POC, that is I is equal to CO2 or H2O or N2 or O2. In the lectures 9 to 12, I have illustrated how to calculate the heat to POC. So, that is how one can calculate the fuel consumption. Now, in many cases, it is also important to know what is the furnace throughput. That is the objective of the fossil fuel combustion is to carry out a metallurgical function. So, there it is also important what is the maximum furnace throughput, and maximum throughput of the furnace, it will not depend on gross available heat, because it will gross available heat will simply tell you that much amount of heat is available to you at the process critical temperature. It will not tell you the throughput. Throughput means, suppose you are heating at 1200 degrees Celsius a slab or bloom, then throughput of the furnace will be the slab or the amount of slab which are coming out at 1200 degrees Celsius. So, their concept of gross available heat is not sufficient, because you are not considering in fuel consumption the losses which are occurring. So, the maximum throughput, or for that matter you are carrying out smelting as a function. So, then we can define the term maximum furnace throughput or smelting power that will be equal to NaH, net available heat generated per unit time upon required net available heat per unit throughput. So, one has to distinguish the fuel consumption and maximum throughput. So, this is about, now here in the fuel consumption we have taken only calorific value of the fuel. In fact, one should also take, suppose if the fuel is preheated, then the heat input will be calorific value of the fuel plus sensible heat of the air or fuel, whatever the case may be. Now, let us consider the factors affecting heat utilization. Factors affecting heat utilization. The first one, air adjustment. air adjustment. This constitute, for example, fuel air ratio, 1:, control, fuel air ratio, percent excess air, air leakage, furnace draft, that is the air adjustment is very important. One has to control the excess air, fuel air ratio and so on. So, for example, if I want to schematically represent how the variation will affect, then this will look something like this. The schematic, here I put percentage of theoretical air. So, somewhere here it is 100, which is the theoretical air. So, this side is excess air and this side is air deficit. That is less than stoichiometric air and more than stoichiometric air. 100, this point is 100, is the stoichiometric amount of air. Now, on the y axis, this is the gross available heat, GAH, in percent of calorific value of fuel. Say at maximum from 0 to 100. So, what we are plotting now, we are seeing the effect of air adjustment on gross available heat, which is expressed in terms of percentage of calorific value of the fuel. Now, of course, if you recall, the gross available heat, which is calculated calorific value minus heat to POC, and heat to POC depends also on the critical process temperature. So, this plot, which is gross available heat in terms of percentage of calorific value of the fuel, if I plot against percentage of theoretical air, then naturally it will be a function of process critical temperature. So, for example, if I take 25 degrees Celsius, then the maximum amount of heat will be available. For example, if I take 25 degrees Celsius as the process critical temperature, there is no heat loss. All the heat will be available to you in the process. Now, less than stoichiometric and more than stoichiometric. So, more than stoichiometric, this value will be constant, nothing will happen. Why it increases? Because as you increase the amount of air, the more and more fuel will be burned and less CO will be formed. At the 100%, which is the stoichiometric amount, the fuel is completely burnt. Therefore, you will be getting the maximum amount of gross available heat. Now, for example, if we take a process critical temperature of 1200 degrees Celsius, this one, and again the gross available heat will drop rapidly. So, this is for the process critical temperature 1200 degrees Celsius. Now, if I take a process critical temperature 400 degrees Celsius, then it will go something like this. And if I take a process critical temperature, say 1600 degrees Celsius, then the drops very rapidly. Now, the temperatures which I have written, it is just to illustrate what happens to the gross available heat if the process critical temperature increases. Say for a given type of fuel, this plot can be generated. If you know the type of fuel, if you know the calorific value, then all that you require is to combust it and calculate gross available heat. So, what this particular graph says, that the gross available heat, it depends on process critical temperature for a given amount of air. Now, suppose if we select a stoichiometric amount of air, then as the process critical temperature increases, the gross available heat decreases naturally, because then the heat taken out by POC will increase because the process critical temperature increases, and therefore, gross available heat will decrease as the process critical temperature increases. Now, the whole idea or the reason for decrease in the gross available heat with the excess amount of theoretical layer, that is, if you go on the right hand side of 100%, then this is essentially due to the excess amount of nitrogen and oxygen which will be available in the products of combustion as you increase the amount of air greater than the stoichiometric amount of air. Now, if the same plot can be used also to calculate the fuel consumption, that means now if I plot now, this is again 100, this is of percent theoretical air, percentage of theoretical air, this is 0, and here I will plot relative fuel consumption say for example meter cube per 1000 kilocalorie heat. So, if I now try to generate a plot of the fuel consumption with the theoretical air, then same way if I have a process critical temperature 25 degrees Celsius, then the fuel consumption will be minimum. This is for 25 degrees Celsius. Now, if I have a process critical temperature at 1600 degrees Celsius, then the fuel consumption will be very high. Naturally, higher is the process critical temperature, more amount of heat will be carried away by the POC, and hence higher amount of fuel will be required in order to carry out the process. Now, if I have for example 400 degrees Celsius, then for the 400 degrees Celsius, this is for the 400 degrees Celsius, and if I have for example 800 degrees Celsius, then, and what is important to know, say if I take say 1200 degrees Celsius, then the fuel consumption it decreases up to the stoichiometric amount, then it drastically increases. This is for 1600 degrees Celsius, then it drastically increases if the process critical temperature is 1200 degrees Celsius. At 400 or 800 degree process critical temperature, the fuel consumption well increases gradually, but at higher temperatures say 1200 or 1600, the fuel consumption increases rapidly, mainly because of the Cp value of nitrogen and oxygen. So, this is how the effect of air adjustment on gross available heat and fuel consumption can be illustrated. However, these all things can be calculated, and I will try to calculate in one or two problem in the subsequent lecture, so that you can understand how to calculate the fuel consumption, how to correlate gross available heat with the fuel consumption, and so on and so forth. We will take few problems so that you can understand. Now, another factor which is important is choice of fuel. Choice of fuel. Changes in fuel analysis. Changes in fuel analysis. Naturally, if you change the fuel analysis, then the caloric value of the fuel will change, and accordingly the gross available heat will be affected, and hence the fuel consumption is also affected. So, third factor is preheating of air and fuel. Now, needless to say that preheating of air and fuel, it brings sensible heat or it is a heat input. So, naturally gross available heat will more as well as fuel consumption will be less, because gross available heat and fuel consumption, they are related to each other. Fourth factor is moisture of air and fuel. Moisture of air and fuel. Now, moisture of the air or fuel, it will increase the fuel consumption, because whatever amount of moisture will be there, it will take away the heat to the process critical temperature. So, that means increase in the moisture content of air or fuel, it will increase the fuel consumption, or other way it will decrease the gross available heat into the furnace. Fifth point is that incomplete combustion. Incomplete combustion. Unburned fuel. They will also affect the heat utilization in furnace, because if there is an incomplete combustion, CO will be produced and the CO will be also raised to the process critical temperature. So, those type of contribution of heat will not be available to the furnace, and if there is an incomplete combustion, then the entire calorific value of the fuel is not available, and accordingly the fuel consumption will be higher and gross available heat will be lower. Similarly, if there is unburned fuel, then corresponding to the amount of unburned fuel, that much amount of energy is not available. So, naturally for incomplete combustion and unburned fuel, the gross available heat will decrease and fuel consumption will increase. Sixth, flue gas temperature. Now, just I will summarize this flue gas temperature, because I have said at many points that higher is the flue gas temperature, more heat will be carried away by the POC, because the heat carried away by the POC is not available to you. Now, the heat carried away by POC is calculated from mCp into TPOC minus T reference. So, TPOC is higher, more amount of heat will be taken by the POC, and hence the flue gas temperature also plays an important role. Of course, one cannot do much because of the requirement that a flue gas temperature has to be equal to that of process critical temperature. If higher is the temperature, flue gas temperature will also be higher. But what one can do is that flue gas temperature should not be higher than the process critical temperature. Now, this condition can occur only when the furnace temperature is not uniform. If some part of the furnace is overheated, then naturally flue gas temperature will be higher than the process critical temperature. So, that point is to be considered. Seventh important point is the oxygen enrichment. Now, this oxygen enrichment is a very important thing. Why? Because when you enrich air with oxygen, you will be decreasing the amount of nitrogen. And as it is known that nitrogen of air is inert, it does not take part in the combustion process. Whatever amount of nitrogen is present in the air, it will take the heat of the fuel and it will go to the as a waste heat. So, if one can reduce the amount of nitrogen by substituting oxygen, then naturally the heat carried by the POC will be less, because oxygen is utilized in the combustion process, whereas nitrogen is an inert. Therefore, it is obvious, it does not require any discussion, that if you enrich air by oxygen, that means if you decrease the 79% of nitrogen to, for example, 70% or 60%, then the nitrogen of the flue gas will be less and less heat will be carried away. So, therefore, oxygen enrichment of air is bound to decrease the fuel consumption and it will increase the gross available heat to the furnace. I mean, it does not require any discussion. Now, this aspect I will take in the next lecture.